So here we have some practice calculations. The Earth's average orbital radius is that. Determine the mass of the Sun. So we have our equation, period, equals 2 pi r to the 3 halves over root gm. Well, we're finding the mass of the Sun, so we want to rearrange a little bit. We can square both sides. We get 4 pi squared r cubed. Move the period over. So if we solve for mass, we get that. So then we can calculate the mass of the Sun, and we're plugging big numbers. Calculator, 1.5 times 10 to the 11th cubed over g times period, which is 365.25 days times 24 hours in a day times 3,600 seconds in an hour. Woo, that's fun, isn't it? And we can type all that in and calculate it away. I didn't have g stored apparently. There we go. So 4 pi squared times 1.5 E11 cubed divided by g times 365.25 times 24 times 3,600 squared. And we get the mass of the Sun is about equal to 2.0 times 10 to the 30th kilograms. It's pretty big. Another example, the Moon Triton orbits Neptune at an average distance of about 3.55 times 10 to the 8th. Neptune's mass, 1.02 times 10 to the 26th. Find the orbital period and orbital velocity. So period, we know 2 pi r to the 3 halves over root gm. So that's going to be 2 pi 3.55 times 10 to the 8th to the 3 halves over root g times 1.02 times 10 to the 26th. So 2 pi times 3.55 E8 caret 1.5 divided by square root of g times 1.02 E26. Oh, extra parentheses. Comes out to about 509,500 seconds. And just as a frame of reference, divided by 3,600 divided by 24, about 5.9 days. And then the velocity would be root gm over r, root g times 1.02 times 10 to the 26th over 3.55 times 10 to the 8th. So g times 1.02 E26 divided by 3.55 E8, about 4,380 meters per second, more or less. Yeah. So we can do calculations of those things. Straightforward. Now a satellite moves in a circular orbit, radius r, period t, speed v. If it was instead to orbit in a circle of radius 2r, what would be its period and speed? Well, period, we know, is proportional to radius to the 3 halves. We can get that from looking at the equation. So if we have 2r, well then our period is going to be 2 to the 3 halves times t, which happens to be 2 root 2 t. Velocity is proportional to 1 over root r. If we look back at our formula for velocity, so if we get 2r, we get 1 over root 2 times velocity. Something that's useful is geosynchronous satellites around the Earth. Satellites orbit with a period of 24 hours. The reason that that's useful is if you put a satellite with a 24-hour orbit in orbit around the equator, then it can stay above the same point on Earth at all times. So it always has the same relative position to the ground, which can be useful. So if we want to find the radius there, well, periods 2 pi r to the 3/2 over root gm. So then r is going to be 2 pi over t root gm to the 2/3. So then we can solve for that. The orbital radius is then 2 pi over 24 times 3600 root g times 5.97 times 10 to the 24th, all to the 2/3. Because now we're orbiting Earth, so our big M is Earth. 2 pi divided by 24 times 3600 times square root of g times 5.97 e24 caret 2 over 3. What in the world? I made a mistake. Derp. I flipped my fraction. I did bad algebra. T root gm over 2 pi. So we'd have to flip these two. So I need to actually take the reciprocal of that answer. That makes more sense. Okay. 4222691.0.18. And this is the distance from the center of Earth. So in order to find the distance above the surface, well, we then need to subtract 6370 kilometers, so minus 6370,000. So how far above the surface of the Earth must it be? That's about 3.6 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. And then what speed does it have to have? Well, we can just go ahead and use this. I stored this value as r in my calculator, so root mass of Earth times g over r. And we can get a value for that. 5.97 e24 divided by r. So that's about 3070 meters per second, more or less. Right. So that's just another thing we can do. You've noticed most of the calculations here have to do with Kepler's third law. An interesting thing that came out of Kepler's third law is the idea of dark matter. You may have heard of dark matter. So Kepler's third law holds, we expect it to hold, and it holds well for our solar system. But we would also expect it to hold for the Milky Way galaxy, for example, or other galaxies, where they have a large amount of mass clustered at the middle and relatively little mass elsewhere. However, if that law held, you know, Milky Way and other galaxies are like a spiral shape, right? So there's these spiral galaxies. So if period squared was proportional to radius cubed, well then as you get farther out, the period would increase. So a galaxy wouldn't hold its shape, right? The stars here, you know, would desync from the stars over here. Like these would go faster and these would lag behind. But as these galaxies rotate, they stay in the same general shape that they're in. So this is where the idea of dark matter comes from, just that there must be more mass that we can't detect. Because from the mass we can detect, you know, we figure Kepler's third law should hold, and so these, you know, stars that are closer inward should be orbiting the galactic center with a smaller period than stars that are farther out. But that doesn't seem to be the case. So scientists say, okay, there must be some mass out there that we're unable to detect. They call it dark matter, and now they're trying to figure out what it could be and figure out how to detect it and stuff like that. Yeah, that's just an interesting little tidbit. All right, the last sort of thing for today is the idea of orbital maneuvers. So you've got a satellite in a circular orbit. You want to move in a larger circular orbit. What's the most efficient way to do this? Now, from third law, we know that a particular speed corresponds to a particular orbital radius for a circle. And based on our second law, we know that objects move fastest when they're closest to the sun or earth or whatever that they're orbiting, and slowest when they're farther out. So how could you make a circular orbit elliptical? Well, we want to go from a smaller circle to a bigger circle, right? So if we've got Earth and we've got a satellite moving in a circle around it, say it's going this way, what would we need to do? Well, what would happen? Objects move fastest when they're closest to the sun or earth or whatever. So if we make this faster right here, suddenly we've increased the speed here. Well, now we have a speed that's faster than the speed that goes with this circular orbit. So what's going to happen? If we make it faster right here, now we're going to be in an elliptical orbit. That'll look like that. So fire rockets at one point. Then you make this elliptical orbit. And then you're now in this elliptical orbit, and you want to transition to a circular orbit. Well, if this is the radius that you want for your circular orbit, now you need to boost up to the speed that corresponds to the circular orbit. So fire rockets again. At the point opposite, we get faster, and that'll put us out into a circular orbit. And that winds up being the most efficient way to transition from a circular orbit to a bigger circular orbit. The same is true if you're going the opposite direction. If you're in a bigger circular orbit, reverse fire your rockets to slow yourself down. That'll drop you into an elliptical orbit, and then reverse fire them again over here to match speed to what the speed that corresponds to that circular orbit. That's interesting. The last little thing here, just again, not non-essential, but for the way the GPS system works, the GPS system has a bunch of satellites up in orbit around the Earth. We'll say this tennis ball is our Earth. And when you use a GPS device, what the device actually does is just kind of sends a ping out to the satellite, okay? And it times that ping. So if you send a ping to a satellite and back, then you detect, okay, or sorry, the other way around. So the satellite sends a ping to the device and then back to the satellite, then it can recommunicate to the device. But so the satellite sends a ping and it comes back, and the satellite knows, okay, it took this long to ping that device, right? Well, that sets a distance from the satellite because we know the speed of light. So the distance from the satellite is such and such. Well, if we have a set distance, well, that could be like here, it could be like here, it could be like here. It could be any point on a circle on Earth, basically. So then you send a ping, another satellite sends a ping and you get a distance, and that gives you another circle, and now you've narrowed your location down to one of these 2 points where the circles interact, and so then you need a third satellite ping to get your third circle to figure out your precise location on the Earth. So you actually need 3 satellites. Based on how the GPS works, you need 3 satellites to determine your location. Just thought that was a little interesting tidbit. And there's the homework.